During an active, multi-vector network breach, an enterprise environment degrades into total chaos. Alerts flood in, services drop, and malicious actors execute scripts across dozens of servers simultaneously in a cascading system failure. To stop the bleeding, human incident responders deploy a strictly serial methodology. They isolate a machine, extract the logs, read the data, form a hypothesis, and then move to the next machine to see if the trail continues. The evidence required to map the attack is physically scattered. A malicious IP lives in network logs. The execution script is buried in a volatile memory dump, and the payload is hidden in the local file system. These are completely isolated data silos. Manually pulling, formatting, and correlating artifacts across these silos takes human analysts immense amounts of time, often days of staring at raw text files to connect a single anomalous login to a specific file execution. Modern enterprises log terabytes of telemetry, but the human serialization bottleneck prevents its effective use. Responders are physically restricted to processing forensic evidence one item at a time. By the time an analyst finishes manually parsing a compromised server's registry, the malware has already propagated through the subnet. Human speed linear processing fails to keep pace with machine speed lateral movement. Aegis-Trace removes the human analyst from the initial response loop entirely, replacing them with an autonomous, multi-agent artificial intelligence swarm designed for concurrent execution. The unified investigative state is a shared Langgraph memory, acting as a central nervous system for specialized agents. Unlike standard AI with context amnesia, the UIS allows agents to simultaneously read and write distinct data blocks to shared memory, maintaining perfect context. But generating connections is useless without mathematical certainty. Aegis-Trace operates on a principle of zero-trust algorithmic forensics. Absolutely no AI-generated hypothesis is accepted into the final report without verified, physical, byte-level proof. By coupling this shared memory state with a zero-trust verification loop, Aegis-Trace executes a 120-second algorithmic autopsy that replaces a 5-day manual process. To successfully automate incident response, a centralized memory state and strict zero-trust verification are the mandatory architectural foundations. We initiate a live scenario at T+0 seconds. The investigator issues a single prompt: find the source of the data leak. Aegis-Trace begins raw ingestion of disk images and network packet captures. At T+10 seconds, the Sentinel agent activates. Its sole mandate is data sanitization and strict integrity control before any analytical reasoning begins. The Sentinel establishes chain of custody, calculating a specific SHA-256 hash string for every artifact. Continuing down the pipeline, we see normalization. It parses chaotic temporal data, UTC, epoch, local time, forcing them into a single, perfectly aligned vertical ISO 8601 timeline. With the timeline secured, the Sentinel chunks these normalized logs into semantic fragments and embeds them into a high-speed QRANT vector database, tagging each with exact metadata offsets. At T+30 seconds, the Scout agent takes over. It queries the vector database, running broad-spectrum baseline comparisons against what a mathematically healthy system should look like. The Scout detects a deviation, an anomalous task scheduler entry executing a hidden script. It flags this finding, successfully logging it as a point of interest, or POI, directly to the central UIS. The system cannot find anomalies in chaos. Standardizing and centralizing disparate data is the strictly required precursor for any autonomous detection. At T+60 seconds, the investigation shifts from sequential data preparation into true parallel swarm execution. The UIS tags the specialized deep diver agent. This specialist focuses exclusively on low-level file system architecture and registry forensics. Triggered by the Scout's newly flagged script, the deep diver executes custom Python tooling to analyze Windows prefetch files and shimcache entries to see exactly when and how that hidden script ran. This split-screen comparison tracks the deep diver's logic. It locates a suspicious LNK file in System32 and reveals a mathematical discrepancy between the file's master file table's standard information timestamp and its file name timestamp. The deep diver has mathematically proven the file was time-stomped by an attacker to look legitimate. At T+90 seconds, we check on the network intelligence agent. It is crucial to note that this agent is operating at the exact same time as the deep diver. The network agent parses the raw PCAP traffic logs. It scans the noise and isolates a sequence of tiny, regular beacons, automated heartbeats communicating outbound to an external command and control server. Using retrieval-augmented generation, the agent queries external threat intelligence feeds, correlating that specific destination IP with known malicious infrastructure. Working backward from that outbound beacon, it maps internal SMB and RDP traffic, aligning lateral movement across the internal subnet to the precise millisecond of the initial external breach. Both the deep diver and the network agent finalize their queries and push their verified points of interest back to the central UIS simultaneously. Because these specialized models analyze memory and network packets concurrently, true multi-agent parallel execution completely eliminates the sequential delays inherent to human investigations. At T+120 seconds, the correlation strategist, the brain of the swarm, reviews the aggregated POIs now waiting in the unified investigative state. The brain executes a chain-of-thought reasoning path. It links the anomalous task scheduler, the time-stomped LNK file, and the Russian C2 beacon into a verified chain of events. Synthesizing these findings, the brain maps the sequence to a specific MITRE ATT attack matrix standard, formatting the behavior into a structured report. But large language models hallucinate. They confidently generate false connections. And in cybersecurity, generative hypotheses fail legal forensic standards. This is why Aegis-Trace utilizes a final component, the verification and grounding auditor. It acts as the ultimate failsafe against AI hallucinations. This diagram illustrates the auditor's proof-of-source test. We see a logic tree tracing the brain's high-level MITRE claim directly down into a raw hexadecimal grid, locking onto the exact 8-character offset byte in the original data dump. The auditor has a strict, uncompromising mandate. If it cannot physically locate the raw byte or line number to support a claim made by the brain, it rejects the hypothesis entirely and forces the swarm back into an investigative loop. Beautifully written, AI-generated intelligence is forensically and legally useless without mathematical, byte-level grounding to back it up. The 120-second timeline concludes. The swarm has successfully compiled a verified, fully documented map of the breach. Having found physical evidence for every assertion, the auditor agent signs off on the final, mathematically grounded incident timeline. Look at this final integration step. The system takes the approved, structured text report, compresses it into a cryptographic hash block, and writes it to a private Hyperledger Fabric instance, locking it securely into a sequential chain. This blockchain ledger acts as a permanent, immutable audit trail. It mathematically guarantees that the AI's logic and the raw data sources it cited remain tamper-proof long after the investigation ends. By utilizing cryptographic ledger storage, the architecture solves the final hurdle for autonomous systems, maintaining a flawless chain of custody. We have tracked the architecture from a fragmented, manual process taking days to a synchronized swarm delivering mathematical proof in exactly 2 minutes. The efficiency of Aegis-Trace relies on the structural power of the Lang-graph-powered unified investigative state, which manages parallel memory so specialized agents can work without blind spots. Accuracy is secured by the auditor, which establishes zero-trust reliability by verifying every generative claim against physical data. Reliable security depends on the ability to provide mathematical and legal proof of an adversary's actions. Aegis-Trace provides a framework for transitioning incident response from subjective estimation to automated byte-level proof.